Hi, so we have set up all the preliminaries needed for a proof of the area formula. In fact, the preliminaries we did were actually just to make this statement well defined. For example, Rademacher's theorem guarantees that this derivative is actually defined almost everywhere, so that its Jacobian is defined almost everywhere. And the linear algebra facts we did will be used in the proof. Okay, so we begin the proof by first looking at the regular part of A. And by that, we precisely mean the set A1, which is a subset of A, where derivative of f at x exists, and rank of the derivative of f of x equals n, the maximum possible. And that is where we expect the image to look more like a manifold than on the degenerate sets where it could crush down to lower dimensions. Okay. We fix a dense subset Tj of linear maps from Rn into Rm. Why is this space separable? If you identify matrices with their matrix representation in the standard bases, then every linear map corresponds to a matrix, and a matrix is just a subset of R to power n squared, or n times m in this case, and that is separable. So there is a countable choice of linear maps that approximate every other linear map. And this closeness of linear maps can be defined in some natural topology, actually a metric, but I'm not going to write it down. Now, we begin an approximation procedure, and as happens very often in geometric measure theory, because you always deal with positive numbers, and also by Lipschitz is an important thing, you usually are better off doing multiplicative approximations than additive ones. So you want to say one quantity is within less than lambda times something and also bigger than 1 over lambda times that other thing. So it's kind of close to the other one. And this is with multiplication rather than adding and subtracting an epsilon. And this is very easy to deal with. But also to make some room, by the way, this proof is based on a joint work I'm doing with Piotr Hajwasz, and I'm not sure in what format it will be published, but so that I acknowledge this. And the whole proof itself is the original proof by Federer, which has been written out with extra details in Evans and Gariepy's book. But anyway, the proof proceeds as follows. So to make some room, we choose some epsilon positive, but it's still small enough such that lambda minus epsilon is still bigger than 1, and lambda inverse, which was less than 1, even if you help with epsilon, it still remains less than 1. Okay. A fact that we haven't really covered, it is kind of a technical thing, is that x going to this derivative of f of x, so we go from Rn into the space of linear maps, is measurable. Again, you have to put a topology on the space of linear maps. This follows because derivatives are basically defined via quotients, and difference quotients of a measurable function are still measurable, and then the limit of measurable sets is measurable. Although here's a continuous limit, there are tricks to make it discrete, And that's why actually I didn't present it, because my Rademacher video was already 50 minutes long, and this would have taken another 10-15 minutes. But it's not really unbelievable result, but still the proof requires some writing down. But anyway, so we take it for granted for this video that x going to derivative is a measurable function. And the easier fact is that a linear map going to the Jacobian, which is given by this determinant L transpose L root, is continuous in that topology of the linear maps. So together they mean that x going to Jacobian of derivative of f of x is measurable. Continuous composed with a measurable function. So that in this integral, this integral is actually well defined. We're integrating a measurable function. So that takes care of measurability of Jacobian, and measurability of the multiplicity function. We will take care of that very carefully and with all the details through the proof. Okay. Now let's fix J and let Bj, which is a subset of my A, be the set of x in A such that, okay, we know Tj is among this list of dense subset of linear maps, so it helps approximate certain other maps. So derivative of f at x is a linear map, and we want to say that it is approximated by this Tj map. And the approximation is in the following sense, which also gives you a hint of how to define the topology on the space of linear map. So when you apply it to V, that's a vector, so you take its norm is less than or equal to lambda minus epsilon, which was a number bigger than 1, norm of Tj applied to V. And on the other hand, we want it to be bigger than lambda inverse plus 1, which was a number less than 1, and then Tj applied to V norm. So this Bj is the set of those points where Tj is the map from the dense collection that helps approximate dfx. Every x you take, the dfx within this error bound will be approximated by some Tj in the list. That means that the union of Bj's, j from 1 to infinity, covers all of A1. So every point x, its dfx is approximated by one of these Tj's by density. So their union covers all of it. Okay, now we want another estimate, and we start with observing that since Tj is a non-singular matrix because it has rank n, a non-singular matrix or linear map equivalently, there exists some positive number Cj such that Tj applied to V norm is always bigger than Cj norm of V. For example, a proof can be given by saying that Tj, this function, from Sn minus 1, let's restrict only to V with norm equal to 1, is continuous, and the Sn minus 1 is compact, so it has a minimum, but this minimum is positive because otherwise Tj would be singular, and that will be the end of it. So there is some positive Cj. For every j, there is Cj with this property. Now, I'm gonna look at points in Bj and again categorize them. So for k, again a natural number, we let dj k, so fixed j, and then dj k will be the set of x's in Bj such that f of y minus f of x minus derivative of f at x times y minus x. Okay, if I divide this by y minus x, then it goes to 0. So after some threshold, I can make that less than any epsilon I want. But for my estimates to work out perfectly, I put this Cj also there. So epsilon is Cj. So for every x, just by definition of differentiability, this does occur after a threshold. djk will be those such that if y is closer to x than delta k equal 1 over k, I include that in my set djk. So for every x, there is some delta that this inequality holds. If the threshold for x is 1 over k, if 1 over k is enough, sufficient for that x, I put it in djk. And again, easily, I already have proven it by saying that every x has some delta x and take those with delta equal to 1k. That would imply that if I take union of djk's over k, then this gives me back all of my bj. So so far I have broken my set A into bj's, and then each bj has been broken into dj's, djk's. So what have I achieved by this decomposition? What I have achieved that for x from djk and y with distance to x less than or equal to 1 over k. So let me also allow equality here without loss of generality. Then from the estimates that I have from this one here and this one here, I get that f of y minus f of x minus df of x applied to y minus x is less than or equal to epsilon tj applied to y minus x norm. So that is what I have for every choice of x from this decomposition and any y within that distance to it. Because I needed this restriction to have this inequality, I'd love to have this inequality for all x and y, but this assumption on their distance doesn't allow me. So what I do, I decompose yet another time. but this time I'm not going to give a new name because I'm going to relabel everything ultimately. So djk is union of sets E such that diameter of E is less than or equal to 1 over k. That's obvious. For any set you give me, I can just write it as a countable union of some of its subsets, each with diameter this much. Write Rn like this and then just intersect. So therefore, for every x now in E and for every y in E, because their difference is less than 1 over k, I get what I wanted with no further restrictions. So minus, sorry, I must say that this 3 holds. Okay, let me go back to this star again. So I have this estimate on Tj, and I have this one. If I apply a triangle inequality, what I get is the following. So for every x again from E, for every y from E, let's do, for example, this version of the triangle inequality. This one will be, so add and subtract, so I subtract df of x at y minus x, take norm, and then I subtracted, now I add it back, d of x, y minus x. Okay, that's triangle inequality. From the 3 star that is right on top of the screen is still, I get that this is epsilon tj y minus x norm. And then from the 1 star inequality I had, d of x is bounded by lambda tj y minus x norm. This was, I think, lambda minus epsilon. Yes, this other one, that's why actually we had epsilon removed, so that now this equals just lambda tj applied to y minus x norm. So what I have succeeded in is comparing this to this. And that's an important inequality. For every x and y from my tiny e, the distance of the images of f itself is bounded by their distance under the linear map tj. So this is just saying that my f has been approximated by a linear map, and that's great news. In fact, we have the other side too. If you just reverse these triangle inequalities, you end up with proving this: f of y minus f of x is bounded by lambda tj applied to this, and bigger than lambda inverse the same quantity. So this is a by Lipschitz approximation of y on the set E, because this holds for every x and every y from my E. Now, these E's, remember, were a decomposition of djk. djk's were decomposition of bj, and bj's were decompositions of a1. Who wants to keep track of all that notation? So after relabeling, we end up with a1 equal to union of some ei's. These are different objects now, such that on each ei, this key estimate let's call this equation B1. So B1 holds with some matrix Ti, but the indexing of Ti's has also been messed up, so it doesn't have to match the index of Ei. But that's not a big deal. So, and believe it or not, all these estimates are so strong that we almost have the area formula. So what do we do? For any I now, from this B1, and saying that it is a bi-Lipschitz estimate, this holds on diameters of stuff and whatnot. So this is a general thing about Hausdorff measure and how it changes under bi-Lipschitz maps. So f of Ei Hn is bounded by, so the Lipschitz constant to power n, because this is Hn of the linear map applied to Ei. And then it's bigger than, similarly, lambda to negative n Hn of Ti of Ei. But Hn of Ti of Ei is equal to, so this was the video on determinants and gram matrices and stuff. This is equal to Jacobian of this linear map times the Lebesgue measure of Ei. And guess what? Ei, I can write it in a more complex way as integrating Jacobian Ti dlnx. I'm integrating a constant value here, nothing crazy there. Jacobian Ti doesn't actually depend on x, but I love to put it in this form. Now, if I put these last two formulas together, well, before that, also we want some estimates on the Jacobian. We have that dfx applied to v norm is bounded by lambda tj applied to v and bigger than lambda inverse tj over v applied to v. From this, we deduce that the Jacobian of dfx is bounded by lambda to power n Jacobian of Ti, or yes, Ti here, and bigger than lambda inverse Jacobian of Ti. For example, this condition implies that the eigenvalues of df are bounded by lambda times eigenvalues of Ti. So this is not a difficult fact to see. Now, from the three inequalities I have, well, two inequalities and one equality I have, I get the following estimate. Integral over Ei of Jacobian Ti dlnx is bounded by dfx. So this holds for every x from my Ei. So this will be integral over Ei, lambda to n, Jacobian Ti dlnx, and bigger than lambda inverse to power n, the same quantity. This actually follows from this, so I always run into conclusions. So from all of this, now I have to say that Hn of f of Ei, remember we bounded this by lambda to power n, Jacobian of Ti times the Lebesgue measure, and then Jacobian is bounded by that other thing, So 2 times lambda to power n comes in, and then here comes EI, and then I have now Jacobian df at x, dln x. So from this I go into Ti, and then from Ti back to df, and that's where I get this estimate. And similarly, I get negative 2n integral over EI of Jacobian dfx, dln x. Okay, one thing that I didn't mention was that all these sets I'm finding in this beginning decompositions are measurable sets. So each EI is measurable. Claim each f of EI, which is a subset of Rm, is Hn measurable. Okay, so the quick proof of this will be that, well, EI is union of a null set and a countable union of compact sets. That's always true for any measurable set. So f of EI will be f of z union of f of ki. I goes from to infinity. Now each fki is compact simply because f is continuous. We don't even need Lipschitz. Where we need Lipschitz is to claim that Hn of f of z is actually 0. I'm going to leave it an exercise. That's very simple. It was in my Hausdorff playlist. So f of EI is Hn measurable. Compact sets are Hausdorff measurable for any dimension, and then this Fc only contributes a null set. Actually, this is true usually. When you have this, if you can manage null sets, then usually you can prove that measurable sets are mapped to measurable sets. And this property that null sets are mapped to null sets is a very important property for functions, and it has its own name. It's called Luzin N condition. But anyway, all we need here is to show that each FEI is Hn measurable. Now, why are we talking about this? So the reason is that at this point, I have the area formula because f on EI is 1 to 1. So this is really just integral of multiplicity over EI y dhny. This is just that. It's equal. And lambda is very close to 1. So this is almost equal to just, so this estimate is trying to give you that this integral is equal to integral of Jacobian over EI. And that is the area formula on the set EI. Because both sides of this are additive, we want to take summation over I. And to take that summation and make sure everything works, we needed to make sure that we have this. Okay, so the details are as follows. Because f restricted to EI is 1 to 1 for every I, the multiplicity of f a1 and y is equal to, so how many points from a1 map to y? Every EI either contributes 1 point or no points at all. So you count all EIs with 0 weight or 1 weight, and that is the characteristic function. So remember, y is picked from Rm, the target. So this summation is exactly telling you if EI has any points that map to y or has none of them. It cannot have two because of this injectivity. So this function is equal to that. Each one of these is a measurable function, hn measurable, because of the claim that we just had. So we can see that n if a1y, y mapping to this, is an hn measurable function defined on Rm. So we can integrate it, and because each one of these are integrable, that integral also goes into summation. That's where I meant I'm going to be super clear and precise when talking about measurability of this multiplicity function. So I've justified why I can integrate this, and I've also justified why the integral switches with I, and this becomes integral Rm of characteristic function of ei times y dhn y. But that is nothing but, you don't have to have disjointness, by the way, for these to work. The disjointness is only an assumption in beginning measure theory to make life easier. So this equals that. Okay, but we have this estimate up here for hn of f of ei. So I'm going to use that blue estimate there. So from the blue boxed, so if you print this out, you won't see it's blue. Estimate above, we have this integral of n of f a1 and y dhn y is less than lambda to 2n. So when I do integration over ei and when I do summation, so it becomes an integral over all ei because they are disjoint. So union of ei is 1. So this will be Jacobian dfx. And over all a1. So this will be d ln of x. And I will have the similar estimate back here. So I've proven the area formula. I've proven that's integral of multiplicity equals integral of Jacobian up to this lambda, but lambda was arbitrary. So let lambda descend down to 1 to prove that integral of multiplicity function a1y dhn y is bounded to, got used to estimates the whole time, and now my lasso doesn't work. Okay, this equals integral a1 Jacobian dfx dln x. End of proof? No, because this is only the area formula for the set A1, which was the regular part of my set A. Okay, so how do we deal with the complementary set? Okay, A minus A1 consists of the set. So what points didn't make it to A1? Where derivative fx does not exist to even talk about its rank, or rank, it does exist, but its rank is strictly less than n. And here comes a theorem that finishes basically the proof, and that is called Sard's theorem. If f from Rn into Rm is Lipschitz, then, okay, let's look at the set X where rank of derivative of f of x is strictly less than n. If you take this set to the image, apply f to it, then Hn of that is 0. Okay, that's a Sard theorem. So if we prove this Sard theorem, we will have the area formula in its complete generality. How? So how does Sard's theorem complete the proof of the area formula? The answer is as follows. Let's call this B2. From B2, this multiplicity function NFAY equals the multiplicity function FA1 and y for Hn almost every y in the target. Because the two multiplicities can differ only if y is in image of a image of this a minus a1. Okay, so that's the only way you can have more points mapping to y from a than points from a1 mapping to y. That if that happens, that means there is some point in a but not in a1 that also maps to y. But Hn of this set, that where they can possibly differ, is 0. That is exactly saying that the two functions are the same almost everywhere. This one is Sard, because part of this set was this critical set, and Sard's theorem gives that, plus image of null sets. So the set where the derivative does not at all exist by Rademacher's theorem is a null set. An image of a null set is Hn null set. We saw it once before with the set Z. Okay, and now that these two functions agree almost everywhere, we see that NFAY is also Hn measurable, because we have shown that the other one is Hn measurable. And now that we can integrate it, because it's measurable, the integral over Rm of this equals integral over Rm of NFA1y dHny. But this quantity we have proven in the first part to be equal to, sorry for my cheap software, unpaid for software, the little prices I pay for using free software. What's going on? Okay, we have shown already from part A of the proof that this is equal to integral over a1 of Jacobian dfx dln x. But then this is equal to integral over a of Jacobian dfx dln x, because on complement of a1, the rank is less than n, and the Jacobian is 0. Or you have a null set, and that also does not contribute to the integral. And this equaling that is exactly the area formula. So this finishes the proof. Modulo Sard's theorem, which isn't an obvious fact at all. So everything is proven in area formula except that we made use of this Sard's theorem, that the image of the critical set has 0 HN measure. Now, in my next video, I will give a proof of this independent of area formula, a completely metric proof. But the proof in Federer's book that we have been following so far, and also expounded in Evans and Gariepy, proves this Sard theorem through a very beautiful perturbation argument. So what is that perturbation argument? Proof of Sard's theorem. Okay, you want to go back to using the area formula. So what you do is this. You define a new function from Rn, this time into Rn times Rm. And when I give you x, you map it to epsilon times x. So you fix epsilon positive. You map it to epsilon x, which is a vector in Rn. And then you map it to f of x in Rm. So originally you had f, and you have now this g. On the critical set of f, which means this set X is where rank is less than n, G in fact does have rank equal to n. The reason being that this epsilon x part already gives you the full rank. So in no direction will the derivative be 0. Well, derivative of f at x will be basically this epsilon times identity matrix n by n, and then derivative of f at x. So even if dfx has 0 rank, or even if it's completely 0 linear map, this epsilon times identity part already completes the full rank criteria. So technically G becomes a full rank matrix. So by first part of proof of the area formula, so before we reached this Sard's theorem, we had already proven the area formula on the regular set. We know that Hn of G of this critical set equals integral over the C of Jacobian of derivative G at x d ln x. I don't need multiplicity function because G is actually 1 to 1. That epsilon x part gives you 1 to 1 this. On the other hand, so how does this relate to f? Notice that f of c equals the projection of G of C, where P1 from Rn times Rm into Rn is this projection, the obvious projection to the first coordinate. And then it's easy to see why f of c equals this one. Notice that P1 is Lipschitz, is in fact 1 Lipschitz. So it only decreases the Hausdorff measure. So Hn of f of c is less than 1 to power n Hn of g of c. So we have this estimate, and we have this equality. But how are we going to show that Hn is actually small or 0? The next observation, or maybe it should be called an exercise because it's not completely obvious. In Evans's book, it's proven by appealing to the fact that the determinant, this Jacobian determinant, is given by the Gauss-Binet formula. We haven't talked about that, and I'm not sure if the things we have talked about are sufficient to give us this. For every x in C, Jacobian of derivative of g at x is proportional to epsilon. So some Lipschitz constant of f, maybe dimension n, times epsilon. So a constant times epsilon where the constant depends only on the Lipschitz constant of f and dimension, but nothing else. And well, the justification is that here in this formula, df lacks one eigenvalue. One eigenvalue is 0. And if we need n eigenvalues in the definition of this determinant, one of them has to come from this part, which provides you with at least one epsilon. If df lacks 2 dimensions, then 2 epsilons enter, but that only helps us. So anyway, for every point from this critical set, Jacobian of dgx is bounded by this epsilon from 1 and 2 then. So from now 2 and 3, we get that Hn of f of c is bounded by integral over c. Well, I have to also say 1 then. Epsilon d ln x. I wish to say that this is less than epsilon Lebesgue measure of c, but if Lebesgue measure of c is infinity, this doesn't help us. That's where we can say without loss of generality. In fact, by working, so it's let's say it's better to say by working with subsets of C at a time, we can assume so this is no good, so we can assume that Ln of C is bounded. You just intersect with increasing sequence of boxes, and for each box you prove measure is 0, then you've proven for everything it's 0. So Hn of f of c, this way we have shown that it's bounded by epsilon Lebesgue measure of c, and now epsilon was arbitrary. Let epsilon go to 0 to see that Hn of f of c, or f of part of c, is 0. And that completes the proof of Sard's theorem, and by extension, proof of the whole area formula. Again, I actually am going to give you a different proof of Sard's theorem, which uses no Jacobians, no Jacobians, and no area formula in its proof. So it's kind of an independent proof. In that way, my conscience will be safe by not justifying this Jacobian estimate. Or maybe I'll do some videos on linear algebra to try to get this. But anyway, there you are. I don't know how many minutes this video became, but I liked it. I did better than I expected, so I have pretty much everything. And this is not an easy proof, to be honest. Evans and Gariepy's book spends about 14 pages on this, but they spend a lot of time on linear algebra, polar decompositions, a Gauss-Binet formula. But still, I think their proof could have been more efficient in some steps. And that's a big claim to make on such a beautiful book. Please put in the comments any questions you have. And thumbs up for the video, the next proof of Sard's theorem. Thanks a lot and have a wonderful day.